A robot just played tennis against a human engineer. Not with a person carefully lobbing balls at a stationary target, an actual rally, with the robot moving across the court, tracking a ball traveling faster than most people can run, and returning shots with precision that would make your local tennis club take notice. The machine stands 4 feet 3 inches tall, weighs 77 pounds, and costs $16,000. That's less than a Honda Civic, less than most people spend on their wedding. And it just learned to play tennis in a way that nobody thought was possible. Before we get into how this happened, we need to talk about why tennis has been such a brick wall for robotics. Because tennis isn't like sorting packages in a warehouse or welding parts on an assembly line. Those are repetitive tasks in controlled environments. Tennis is chaos wrapped in physics. A tennis ball can reach speeds of 67 miles per hour in casual play. Professional serves break 100 miles per hour. The ball is in the air for fractions of a second. Contact between racket and ball lasts 4 milliseconds. 4. That's less time than it takes to blink. During those 4 milliseconds, the robot has to control wrist angle, racket face orientation, swing speed, follow-through direction, and body positioning to ensure it doesn't fall over from the momentum of its own swing. And that's just hitting the ball. To actually play tennis, you need to predict where the ball is going based on incomplete information. You need to move your entire body to the right position. You need to time your swing to intercept a moving target. You need to recover your balance after the strike. And you need to do all of this while a human opponent is actively trying to put the ball where you're not. For years, roboticists have been trying to crack this problem. The standard approach has been to capture perfect human motion data. Strap sensors all over a professional tennis player. Record every joint angle, every muscle activation, every subtle weight shift. Then try to translate that data into robot movements. It doesn't work. Capturing a tennis player's full motion during an actual match is nearly impossible. Players run across a court that's 78 feet long and 27 feet wide. Motion capture systems struggle with that kind of range. And even when you do capture the data, you run into the embodiment problem. A human body and a robot body are fundamentally different. Human wrists can rotate in ways robot wrists can't. A human shoulders have range of motion that robot shoulders don't. Copying the motion doesn't give you the skill. Some teams tried using video footage from tennis matches, feeding it into AI systems that could extract movement patterns. But broadcast footage is shot from the sidelines, from behind the baseline, from overhead. The camera angles change constantly, the lighting shifts, players move in and out of frame. Extracting precise joint angles from that kind of data is like trying to rebuild a watch by looking at a blurry photograph. A few robots have been trained to play simpler sports. Table tennis robots exist. They work because the playing area is small, the ball moves in predictable arcs, and the robot can be bolted to the floor. Football robots have been demonstrated, but they move slowly, and their ball control looks robotic in the worst sense. Nothing had come close to the dynamic, reactive, full-body coordination that tennis demands. Then a team of researchers from Tsinghua University and Peking University, working with a Chinese AI robotics company called Galbot, decided to try something different. Instead of chasing perfect data, they used imperfect data. Instead of recording complete tennis matches, they captured fragments. Short clips of basic movements, forehands, backhands, side shuffles, crossover steps. They recruited 5 amateur tennis players. Not professionals, not college athletes, just people who play tennis at a level you'd find at a public park on a Saturday morning. They set up a compact motion capture area, roughly 10 feet by 16 feet. That's more than 17 times smaller than a regulation tennis court. And they recorded 5 hours of movement fragments. The data was messy, the movements were imperfect. The technique was inconsistent. But here's the insight that changed everything. Imperfect data still contains information about how humans move. Even an amateur's forehand captures something essential about weight transfer, hip rotation, and racket acceleration. The fragments didn't need to be perfect. They needed to be real. The team built a system called LATENT. The acronym stands for Learning Athletic Humanoid Tennis Skills from Imperfect Human Motion Data. The system works in layers. The first layer is a motion tracker. This takes the raw human movements and translates them into actions a robot can perform. It's not copying the motion. It's learning the principle behind the motion. When a human shifts weight from their back foot to their front foot during a forehand, the tracker figures out what the robot equivalent of that weight shift looks like. The robot's legs are different lengths. Its center of mass is in a different place. Direct copying would fail. Translation succeeds. The second layer is what they call a latent action space. Instead of learning every possible joint configuration for every possible situation, the system learns compressed representations. It learns the essence of a forehand. Not the thousands of specific joint angles, but the underlying pattern. This lets the robot generate movements it has never seen before. If it learned a forehand from the baseline and a forehand from midcourt, it can interpolate and create a forehand from three-quarters court. The third layer is the high-level policy. This is the brain. It tracks the ball, predicts the trajectory, decides what type of shot to use, and coordinates the entire body to execute. It's making decisions 500 times per second. Ball position, ball velocity, robot position, distance to ball, time to contact, optimal strike point, required racket angle, body orientation, footwork sequence. All of this processed faster than human conscious thought. But here's where it gets interesting. The researchers knew that wrist control is one of the hardest parts of tennis. The subtle rotation that makes the difference between a good shot and a ball sailing out of bounds. A human wrist motion during a tennis swing is so nuanced that even high-quality motion capture struggles to record it accurately. And the difference between a human wrist and a robot wrist makes direct copying impossible. So they built a workaround. The high-level controller directly adjusts the robot's wrist during play. Instead of relying on the imperfect training data for wrist angles, the system computes the correct wrist position in real time based on where the ball is and where it needs to go. This is a clever acknowledgement of the system's limitations. They didn't pretend the data was perfect. They identified the weak point and compensated for it. The entire system was trained in simulation, not on a physical robot, in a virtual environment where the team could run millions of practice rallies. But here's the critical part. They didn't make the simulation perfect. They made it messy. They randomized everything: the robot's weight, the ball's mass, friction coefficients, aerodynamic drag. They added noise to the sensor readings. They introduced frame drops to simulate the robot's camera's missing data. They added latency to mimic the delay between when the robot sees the ball and when it can react. This technique is called domain randomization. By training in an environment that's harder and more unpredictable than the real world, the robot learns to handle imperfection. When it finally steps onto a real tennis court, the real world seems easy by comparison. The results in simulation were striking. 97% success rate on forehand shots, 82% on backhands. The system could sustain rallies of up to 25 consecutive shots when two robots played against each other. But simulation success doesn't guarantee real-world performance. Plenty of robots work beautifully in virtual environments and fall apart the moment they encounter actual physics. So the team deployed the system on a real Unitree G1 robot. This is where the hardware matters. The G1 was released in 2024 by Unitree Robotics, a Chinese company that started out making quadruped robots. Four-legged machines that could run, jump, and navigate rough terrain. When they moved into humanoid robotics, they brought that same focus on dynamic movement. The base model G1 has 23 degrees of freedom. That's 23 independent axes of movement across the entire body, 6 per leg for walking and balance, 5 per arm for reaching and manipulation. The torso can rotate. The head can turn. For the tennis version, they used a higher spec configuration with up to 43 degrees of freedom. Additional joints in the wrists. Extra range in the waist. A 3-fingered dexterous hand that can grip a tennis racket. The robot's joints are driven by permanent magnet synchronous motors. These are the same type of motors used in Unitree's quadruped robots. They're built for fast response and efficient heat dissipation. The knee actuators can deliver up to 120 Newton-meters of torque in the advanced models. That's enough force to lift the robot's own weight repeatedly without overheating. For sensing, the G1 uses a Livox Mid 363D LiDAR and an Intel RealSense D435 depth camera. The LiDAR creates a point cloud of the environment, millions of distance measurements per second. The depth camera adds visual detail. Together, they give the robot a real-time understanding of where everything is in three-dimensional space, including the tennis ball. But tracking a tennis ball is harder than it sounds. The ball is small, it moves fast. It can be occluded by the net, by the robot's own body, by shadows on the court. To handle this, the system uses a clever trick. It maintains a 4-frame sliding window. Instead of trusting the ball position from a single frame, it averages the position across 4 consecutive frames. This smooths out noise and gives a more reliable velocity estimate. The processing happens on an 8-core CPU for basic motion control, with an optional NVIDIA Jetson Orin NX module for the advanced AI. The Jetson delivers 100 TOPS of AI processing power. TOPS stands for trillions of operations per second. That's enough computational muscle to run the entire perception, planning, and control pipeline in real time with latency measured in milliseconds. The robot's battery lasts about 2 hours of active movement. Not enough for a full tennis match, but enough for extended testing sessions. And the G1 can fold down to fit in a large suitcase. You could pack it up, take it to a tennis court, unfold it, and start playing. The logistics are almost as impressive as the technology. When the team finally tested the system in the real world, they set up a rally scenario. A human engineer on one side of the net, the G1 on the other. The human hits the ball. The robot tracks it, moves to intercept, and returns the shot. Then it repositions for the next ball. The success rate in real-world testing was 91% for forehands and 78% for backhands. Those numbers are lower than the simulation results, which is expected. The real world always introduces complications that simulations miss. But they're still remarkably high for a robot performing a task this dynamic. What struck observers most wasn't just that the robot could hit the ball, it was how the robot moved while doing it. The footwork looked natural. Not human exactly, but not stiff either. The robot shuffled laterally across the court. It adjusted its positioning based on the incoming ball. It recovered its balance after each swing and transitioned smoothly back into a ready position. The video that Galbot posted online shows the robot sustaining a multi-shot rally. The human isn't making it easy, but he's not making it impossible either. The balls are coming in at moderate speed, around 33 to 50 feet per second. That's amateur club tennis pace. Not gentle, but not aggressive either. And the robot is keeping up. There's a moment in the video where the ball comes in slightly to the robot's left. The robot pivots, takes 2 quick side steps, lines up the shot, and returns it cross-court. The entire sequence happens in less than 2 seconds. Track ball, plan movement, execute footwork, time swing, strike ball, recover balance. All of it coordinated by a system that learned from 5 hours of imperfect human data. But let's be clear about what this demonstration actually is. This is not a robot that can beat a professional tennis player. This is not a robot that's ready to compete in a tournament. The human in the video is feeding relatively predictable balls. He's not mixing up spin, speed, and placement to throw off the robot's timing. He's not rushing the net or hitting drop shots. This is a controlled test that proves the concept works. The researchers are transparent about the limitations. The current system focuses on returning balls to target locations. It doesn't play strategic tennis. It doesn't construct points. It doesn't adapt to an opponent's weaknesses or disguise its own shots. And it still relies on external motion capture systems to track the ball. The robot isn't using only its onboard cameras. There are external sensors providing ball position data. The team's next goal is to incorporate active vision. Let the robot track the ball using only what it can see through its own cameras. This is harder than it sounds. A tennis ball is about 2.6 inches in diameter. At 50 feet per second, it's covering that distance in 20 milliseconds. The robot's cameras need to detect the ball, estimate its position in 3D space, and compute its velocity, all while the robot itself is moving. They also want to move beyond the return task and into actual match play. This means the robot would need to serve. It would need to anticipate where the opponent is going to hit the ball based on their body position and racket angle. It would need to understand court geometry and shot selection. Return a ball deep to the baseline to push your opponent back. Hit a short ball to pull them forward. Mix up the pace to disrupt their rhythm. But even with these limitations, what the latent system demonstrates is a breakthrough in how robots can learn physical skills. For years, the robotics community has been stuck on the data problem. You need perfect data to train perfect robots. Except perfect data is expensive, time-consuming, and often impossible to collect. Latent proves you don't need perfect data. You need good enough data and a smart way to use it. 5 hours of amateur players performing basic movements was enough to teach a robot to play tennis at a level that would surprise most people. That same approach could work for other sports: soccer, basketball, volleyball. Any activity where capturing complete professional-level motion data is impractical. The implications go beyond sports. Teaching a robot to play tennis involves the same fundamental challenges as teaching a robot to navigate a disaster site, assist in surgery, or work alongside humans in a factory. Dynamic environments, fast reactions, whole-body coordination, adapting to unpredictable situations. The skills transfer. This is why companies like Figure, Agility Robotics, and Tesla are investing billions into humanoid robotics. It's not about making robots that look like humans for aesthetic reasons. It's about making robots that can operate in environments built for humans. Stairs, doorways, ladders, vehicles, tools. All of it designed for a bipedal body with 2 arms and 2 hands. Boston Dynamics has been working on their Atlas robot for over a decade. Atlas can do backflips. It can parkour across obstacle courses. It can lift 50-kilogram loads and navigate rough terrain. But Atlas costs an estimated $140,000 to $150,000, and until very recently it was purely a research platform. Commercial deployments are just starting in 2026. Tesla's Optimus is targeting a price point of $20,000 to $30,000. That's more affordable, but Optimus is still in the prototype phase. The robots Tesla has shown publicly can walk, pick up objects, and perform simple tasks, but they're not ready for widespread deployment. Tesla is aiming for thousands of units by the end of 2026, but those will be used internally in Tesla factories, not sold to consumers. The Unitree G1 is shipping now. Universities, research labs, and robotics companies around the world have already received units. The base model starts at $16,000. The education version with full SDK access and higher spec hardware costs more, but it's still a fraction of what Boston Dynamics charges. This is the first time a humanoid robot with serious dynamic capabilities has been available at a price point accessible to small teams and independent researchers. And Unitree isn't stopping at tennis. In February 2026, dozens of G1 robots performed at China's Spring Festival Gala in front of 679 million viewers. They did drunken fist kung fu. They handled nunchucks. They executed spinning staff combinations. The highlight was a catapult launch where robots were thrown 3 meters into the air, performed mid-air backflips, and landed stably on stage. There was no safety net, no reset button. A single fall would have been broadcast to hundreds of millions of people. But the robots absorbed the kinetic energy, adjusted their orientation mid-flight, and stuck the landing. This wasn't just a tech demo. It was a demonstration that the technology is reliable enough to perform live in front of a global audience. Unitree's CEO Wang Xingxing revealed that the team ran hundreds of millions of training iterations in simulation before the robots ever touched the stage. They were teaching the AI how to manage angular momentum in mid-air, how to reposition limbs to control spin rate. The same simulation-to-real pipeline that made the tennis robot work made the gala performance possible. But here's what makes the tennis demonstration different from the gala performance. The gala was a scripted routine. The robots knew exactly what movements to execute and when. Tennis is reactive. The robot doesn't know where the ball is going until the human hits it. Every rally is different. Every shot requires a new decision. This is the difference between a choreographed dance and improvisation. The Latent team published their research paper in March 2026. They've open-sourced the code on GitHub. Other robotics teams can now download the training pipeline, load their own motion capture data, and teach robots new skills. This is how progress accelerates. One team makes a breakthrough. They share it. Other teams build on it. Within 6 months, someone will use this framework to teach a robot to play soccer. Within a year, someone will adapt it for industrial assembly tasks or search and rescue operations. There's a concept in robotics called the sim-to-real gap. This is the difference between how a robot performs in simulation and how it performs in the real world. Simulations are clean. Physics engines calculate forces and trajectories with mathematical precision. Real-world physics is messy. Friction varies. Surfaces deform. Sensors have noise. Motors have backlash. Closing the sim-to-real gap has been one of the hardest problems in robotics. The latent approach closes that gap by making the simulation harder than reality. Train in chaos, deploy in order. It's the robotics equivalent of training at high altitude. When you come back down to sea level, everything feels easier. This is also why the price matters. At $16,000, the G1 is accessible to university labs that don't have million-dollar research budgets. It's accessible to startups working on new applications. It's accessible to individual researchers who want to experiment with humanoid robotics. When the barrier to entry drops, the pace of innovation increases. Goldman Sachs research projects that 50 to 100,000 humanoid robots will ship globally in 2026. China is leading that surge. Agibot, another Chinese company, rolled out their 5,000th mass-produced humanoid robot in late 2025. By early 2026, they're shipping thousands more. Unitree is projecting deliveries of 10 to 20,000 G1 units in 2026 alone. This is the BYD moment for robotics. Just as Chinese EV manufacturers disrupted the global car market by scaling production and slashing prices, Chinese robotics companies are doing the same to humanoids. Shenzhen's Robot Valley has vertical integration that no other region can match. You can source motors, sensors, alloy panels, and chips within a 20-minute radius. If you need a custom servo, you can have a prototype manufactured and delivered the next day. Western companies are focusing on specialized, high-cost solutions for specific enterprise applications. Chinese companies are focusing on the fleet. Not one perfect robot. 1 million good enough robots. And as the tennis demonstration shows, good enough is already capable of tasks that seemed impossible just a few years ago. The question that remains is where this goes next. If a robot can learn to play tennis from 5 hours of amateur data, what else can it learn? Surgery from watching surgical residents? Construction work from observing framers on a job site? Elderly care from watching professional caregivers? The latent framework suggests that the bottleneck isn't the robot's physical capability anymore. It's our ability to give the robot useful learning experiences, and that bottleneck is dissolving fast. Every robotics lab, every company working on humanoids, every researcher with access to a G1 is now contributing to a global dataset of how robots can move, interact, and perform in the real world. When you watch that video of the G1 playing tennis, you're not just watching a robot hit a ball. You're watching the moment when learning from imperfect data became good enough to solve problems that perfect data couldn't. You're watching the moment when a $16,000 robot demonstrated capabilities that were supposed to require $100,000 research platforms. And you're watching the beginning of a shift where the physical world becomes as trainable, as adaptable, and as rapidly evolving as the digital world has been for the past 2 decades. The robot isn't perfect, but it doesn't need to be. It just needs to be good enough to learn. And once a robot can learn, the only question is how fast.